For 70 years, we believed our closest stellar neighbor was harmless, a tiny, dim red dwarf floating just 4 light-years away. Too cool to threaten anything, too small to matter. We were catastrophically wrong. Proxima Centauri is not the quiet neighbor we imagined. It is a stellar furnace of violence masquerading as a fading ember. Scientists have now confirmed that this star bombards its surrounding space with radiation levels that would sterilize any world orbiting it thousands of times over during its lifetime. The danger was never sudden. It was cumulative, constant, and completely overlooked because we measured the wrong things for the wrong amount of time. If you want to understand how we got our closest star so wrong, hit that like button and subscribe. Let's begin. Look up at the night sky and find the constellation Centaurus. Somewhere within that ancient pattern of stars lies an object so faint that no human eye has ever seen it without technological assistance. This invisible speck of light is Proxima Centauri, the closest star to our solar system beyond the Sun. At just 4.24 light-years away, it represents our nearest stellar neighbor in a galaxy containing 400 billion stars. For most of human history, we did not even know Proxima Centauri existed. The star is so dim that it escaped detection until 1915, when Scottish astronomer Robert Innes spotted it during a photographic survey of the southern skies. Even then, scientists considered it unremarkable. A tiny red dwarf barely visible through professional telescopes. The kind of star you catalogue and forget. This initial dismissal set the tone for everything that followed. Proxima Centauri entered scientific consciousness as an afterthought. A cosmic footnote. The smallest, dimmest, most forgettable type of star in the universe happened to be our closest neighbor. Astronomers treated this proximity as a curiosity rather than an opportunity. After all, what could we possibly learn from such an insignificant stellar ember? This assumption represented the first fundamental error in our understanding of Proxima Centauri. We mistook dimness for harmlessness. We confused small size with gentle behavior. We projected human intuitions about fire and heat onto a stellar object that operates according to physics we barely understood at the time of its discovery. The numbers seem to support our dismissal. Proxima Centauri measures approximately 1/7 the diameter of our Sun. Its mass equals roughly 1/8 of solar mass. The surface temperature hovers around 3,000 degrees Celsius, compared to the Sun's 5,500 degrees. Most significantly, Proxima produces only approximately 1/6 of 1% of the Sun's total light output. Imagine holding a candle next to a searchlight. That comparison understates the difference between Proxima Centauri and our Sun. The star that serves as our closest cosmic neighbor generates so little visible light that it would appear as a dim red point even to observers standing on a planet orbiting within its habitable zone. This extreme dimness shaped every assumption scientists made about Proxima Centauri for decades. Small stars produce less energy. Less energy means less radiation. Less radiation means less danger to any planetary environments that might exist nearby. The logic seemed airtight. Red dwarfs represented the cosmic equivalent of dying embers, safe, stable, and fundamentally boring. But this brings us back to the star itself, and the critical error embedded in our reasoning. We measured Proxima Centauri using standards developed from studying our own Sun. Solar physics dominated 20th century stellar astronomy because the Sun was the only star we could observe in detail. Every instrument, every model, every assumption about stellar behavior emerged from our intimate knowledge of one particular yellow dwarf star located at the center of our solar system. The Sun is remarkably well behaved by cosmic standards. It produces steady radiation output with variations of only about 1/10 of 1% over its 11-year activity cycle. Solar flares occur, sometimes dramatically, but they represent brief interruptions in an otherwise calm stellar environment. The Sun has maintained this relative stability for approximately 4.5 billion years. Scientists naturally assumed that smaller, cooler stars would be even more stable. If the Sun behaves calmly, surely a star producing less than 1% of its energy output would behave even more calmly. This assumption felt intuitive and reasonable. It was also completely wrong. The mischaracterization of Proxima Centauri began with this solar-centric thinking. We asked what a star like our Sun would look like if it were smaller and cooler. We did not ask what an entirely different type of stellar object might actually do. Red dwarfs operate according to fundamentally different physics than yellow dwarfs like our Sun. The internal structure differs dramatically. Energy transport mechanisms follow alternative pathways. Magnetic field generation occurs through distinct processes. None of this was well understood when Proxima Centauri was discovered. Even as stellar astrophysics advanced through the 20th century, red dwarfs received relatively little attention. They were too dim to observe easily. They seemed too boring to justify expensive telescope time. The few observations that did occur captured only brief snapshots of stellar behavior, spanning days or weeks rather than years or decades. This observational bias created a profound blind spot in our understanding. The star we thought we knew bore little resemblance to the star that actually exists. Consider the fundamental challenge facing early 20th century astronomers. They possessed telescopes capable of detecting Proxima Centauri as a point of light. They could measure its position relative to background stars. They could estimate its distance through parallax observations. But they could not study its surface features. They could not monitor its activity patterns continuously. They could not detect emissions in wavelengths beyond visible light. Every conclusion drawn about Proxima Centauri during this period relied on inference rather than direct observation. Scientists measured what little light reached their instruments and constructed theoretical models to explain that measurement. This assumption was never tested, because the technology to test it did not exist. The astronomical community developed an implicit hierarchy of stellar importance during the early 20th century. Massive blue giants commanded attention because they dominated the night sky with brilliant luminosity. Yellow dwarfs like our Sun received study because one happened to sit close enough for detailed observation. White dwarfs fascinated theorists because they represented exotic endpoints of stellar evolution. Red dwarfs occupied the bottom of this hierarchy. They produced too little light to observe easily from Earth. Their physics seemed too mundane to justify dedicated research programs. Their prevalence in the galaxy made individual objects seem interchangeable and therefore unimportant. This prejudice against small dim stars created systematic gaps in astronomical knowledge. While scientists developed sophisticated models of massive stellar interiors and published detailed analyses of solar surface activity, red dwarf physics remained largely theoretical. The assumptions embedded in early characterizations of Proxima Centauri went untested for decades. The first hints of trouble emerged in the 1950s when astronomers detected unusual brightness variations from Proxima Centauri. The star would occasionally flare, increasing its brightness by significant factors before returning to baseline. These flares seemed concerning at first, but scientists quickly rationalized them away. All stars flare occasionally, they argued. The Sun produces flares. Even calm stars experience periodic outbursts. A few dramatic events do not change the fundamental nature of a stellar object. Proxima Centauri remained classified as a quiet red dwarf with occasional disturbances. This classification persisted for decades, despite accumulating evidence that something was wrong. Observers noted that Proxima Centauri flared more frequently than expected. The flares reached higher intensities than similar stars. The intervals between major events seemed shorter than models predicted. Each observation that challenged the prevailing view was absorbed and explained away. The star was going through an active phase. The detection methods were improving, revealing events that always occurred but were previously missed. The sample size remained too small for statistical significance. What scientists failed to recognize was a pattern emerging from the data. Proxima Centauri was not experiencing occasional disturbances in an otherwise calm existence. The star was actively hostile in ways that continuous observation would eventually reveal. The problem extended beyond simple flare frequency. Unlike the Sun, which has distinct radiative and convective zones, Proxima mixes its entire stellar material from core to surface. This convection pattern drives magnetic field generation through a process called a turbulent dynamo. To understand why this matters, consider how the Sun generates its magnetic field. Our star has a radiative core where energy moves outward through photon absorption and re-emission. Surrounding this core sits a convective zone, where hot plasma rises toward the surface while cooler material sinks. The boundary between these zones creates conditions for organized magnetic field generation through differential rotation. Proxima Centauri lacks this clean separation. The entire star convects from center to surface. Hot material rises chaotically. Cool material descends unpredictably. The resulting fluid motions generate magnetic fields through turbulent processes that lack the organization present in solar magnetic activity. The magnetic implications proved enormous. Proxima Centauri generates magnetic fields that cover a far larger fraction of its surface than the Sun's magnetic regions. These fields are not stable. They twist, reconfigure, and release energy through violent magnetic reconnection events. The star essentially wraps itself in tangled magnetic loops that periodically snap and release stored energy. This magnetic architecture makes flaring not an exception, but the normal state of stellar operation. Proxima Centauri does not occasionally erupt. It constantly erupts at varying intensities across its entire surface. The calm periods between major flares are themselves filled with smaller eruptions that previous instruments could not detect. Understanding this required observational capabilities that did not exist until recently. 20th century telescopes captured visible light from Proxima Centauri and detected the brightest flares when the star's optical output temporarily increased. What these instruments missed was everything happening in wavelengths beyond visible light. The electromagnetic spectrum extends far beyond what human eyes can perceive. Gamma rays carry the highest energies, followed by X-rays, ultraviolet radiation, visible light, infrared emission, microwaves, and radio waves. Each wavelength range reveals different physical processes occurring in stellar atmospheres and interplanetary space. Proxima Centauri produces significant output across this entire spectrum, with the most energetic emissions occurring in wavelengths invisible to optical telescopes. The dim red glow that ground-based observers detected represented only a tiny fraction of the star's actual radiation output. When space-based X-ray observatories finally turned their attention to nearby red dwarfs, the results shocked researchers. Proxima Centauri was not quiet at all. In X-ray wavelengths, the star blazed with activity that dwarfed its visible light output in relative terms. The dim ember we thought we knew was actually a source of intense high-energy radiation. The Rosat satellite provided some of the first detailed X-ray observations of Proxima Centauri during the 1990s. Researchers detected baseline X-ray emission far exceeding what models predicted for such a small cool star. More disturbing were the frequent X-ray flares that sent emission levels spiking by factors of 10 or more above baseline. These observations should have triggered immediate reassessment of our assumptions about red dwarf behavior. Instead, scientists compartmentalized the information. X-ray emission was interesting but seemed like a specialized phenomenon, relevant only to high-energy astrophysics. The fundamental characterization of Proxima Centauri as a small, harmless neighbor persisted in popular and even professional understanding. The disconnect between specialized knowledge and general perception allowed the mischaracterization to continue. Experts studying X-ray astronomy knew Proxima Centauri was active. Experts studying planetary formation assumed it was calm. These communities rarely communicated effectively, allowing contradictory assumptions to coexist without resolution. Academic specialization contributed to this communication failure. Researchers who devoted careers to X-ray observations of stellar coronae, published in journals read primarily by other X-ray astronomers. Researchers modeling planetary atmospheres and habitability conditions read different journals and attended different conferences. Each community developed increasingly sophisticated understanding of phenomena within their specialty, while remaining largely ignorant of developments in adjacent fields. This fragmentation of knowledge allowed dangerous misconceptions to persist far longer than they should have. The information needed to correctly characterize Proxima Centauri existed within the astronomical community. It simply failed to propagate across disciplinary boundaries in ways that would have forced reassessment of prevailing assumptions. Meanwhile, Proxima Centauri continued doing what it had always done. The star produced flares ranging from minor brightness fluctuations to catastrophic events releasing more energy than our Sun produces in normal operation over extended periods. The intervals between major flares varied unpredictably from hours to days to weeks. The radiation output in ultraviolet and X-ray wavelengths maintained levels that would devastate any Earth-like atmosphere exposed to them. None of this behavior was new. Proxima Centauri had operated this way for billions of years. The star formed approximately 4.85 billion years ago, slightly before our own Sun ignited. Throughout its entire existence, it has been actively bombarding surrounding space with energetic radiation and particle emissions. We simply failed to notice because we were looking at the wrong things. The visible light output of Proxima Centauri told us almost nothing about its true nature. The dim red glow that made the star seem harmless was merely the most easily detected component of a far more complex and dangerous emission spectrum. By focusing on what we could see most easily, we missed what actually mattered. This pattern of selective observation created a scientific illusion. We built mental models of Proxima Centauri based on incomplete information interpreted through inappropriate frameworks. The star appeared safe because we defined safety in terms of visible light output. It appeared stable because we measured stability over timescales too short to reveal true behavior patterns. The timescale problem deserves particular attention. Human observations of Proxima Centauri span roughly 1 century. The star has existed for approximately 4.85 billion years. Our observational window represents less than 1/50 millionth of the star's lifetime. Imagine trying to understand human behavior by observing a single person for 1/20th of a second. You might catch them blinking. You might catch them mid-sentence. Whatever you observed would tell you almost nothing about the full range of human activity. Yet this is essentially what we attempted with Proxima Centauri during the early decades of observation. Even modern continuous monitoring campaigns spanning years to decades capture only infinitesimal fractions of stellar history. We extrapolate from these brief windows to make claims about behavior patterns spanning billions of years. Sometimes these extrapolations prove valid. Sometimes they produce catastrophically incorrect conclusions. The danger was always there. We just convinced ourselves it did not exist. This self-deception had real consequences when scientists began considering the possibility of planets orbiting Proxima Centauri. If the star was truly calm and stable, its habitable zone might support worlds capable of developing and maintaining life. The proximity of such worlds to Earth would transform our understanding of cosmic habitability. The search for exoplanets around Proxima Centauri began in earnest during the 1990s and 2000s. Astronomers employed radial velocity techniques that detect the gravitational wobble a planet induces in its parent star. Early results proved inconclusive. The star's intrinsic variability complicated efforts to identify the periodic signals that orbiting planets would produce. This variability itself should have served as a warning sign. A star that shows significant brightness, fluctuations, and spectroscopic variations does not provide a stable environment for planetary systems. The very characteristics that made planet detection difficult around Proxima Centauri indicated the challenging conditions any detected planet would face. Nonetheless, the search continued. Finding a planet around our nearest stellar neighbour represented too significant a milestone to abandon due to mere observational difficulties. The prestige and funding associated with such a discovery motivated sustained effort, despite accumulating evidence that any detected planet would face severe environmental challenges. The discovery of Proxima Centauri b in 2016 seemed to validate these hopes. A planet orbiting within the star's habitable zone, receiving similar amounts of total energy that Earth receives from the Sun. Media coverage celebrated the finding as evidence that habitable worlds might exist practically next door to our solar system. The detection relied on radial velocity measurements, accumulated over years of observation. The star showed a periodic wobble, consistent with a planet roughly 1.3 times Earth's mass orbiting at approximately 7.5 million kilometers. This orbital distance placed the planet within the zone, where liquid water could theoretically exist on a planetary surface. Headlines proclaimed the discovery of a potentially habitable world just 4 light-years away. Popular articles speculated about future missions to explore our cosmic neighbour. The public imagination embraced the possibility that life might exist so close to our own solar system. What this coverage largely ignored was everything scientists had learned about Proxima Centauri's true behaviour over the preceding decades. The calm, stable star that might nurture life did not match the violent, active star that X-ray observations revealed. The habitable zone calculations assumed a friendly stellar environment that actual measurements contradicted. The habitable zone concept itself requires examination. Astronomers define this zone as the range of orbital distances where a planet could maintain liquid water on its surface, given certain assumptions about atmospheric composition and planetary characteristics. The inner edge marks where a runaway greenhouse effect would boil away surface water. The outer edge marks where carbon dioxide would condense into dry ice, preventing sufficient warming. These boundaries depend entirely on stellar luminosity. A dim star like Proxima Centauri has a habitable zone much closer than a bright star like our Sun. Proxima's habitable zone extends from roughly 5 million to roughly 9 million kilometers from the star. Compare this to Earth's orbital distance of 150 million kilometers from the Sun. The proximity required for habitability around red dwarfs creates immediate problems that habitable zone calculations typically ignore. Planets orbiting so close to their stars experience tidal forces that likely synchronize their rotation with their orbital period. One face permanently points toward the star, while the other faces eternal darkness. This creates extreme temperature gradients that challenge atmospheric stability. More significantly for our discussion, the close orbital distances place planets directly in the path of stellar radiation at intensities that diminish only slowly with distance from the source. The inverse square law governs how radiation spreads through space. Double the distance and radiation intensity drops to 1/4. But when starting distances are measured in millions of kilometers rather than hundreds of millions, even substantial increases in orbital distance provide limited protection. Proxima Centauri b orbits approximately 7.5 million kilometers from its parent star. This distance places it firmly within the nominal habitable zone, where liquid water could theoretically exist. It also places it directly in the path of stellar radiation that makes the Sun's output look gentle by comparison. The planet completes one orbit every 11.2 Earth days. This tight orbital period means Proxima Centauri b lies far closer to its star than Mercury does to our Sun. Mercury orbits at an average distance of 58 million kilometers, nearly 8 times farther from the Sun than Proxima b orbits from Proxima Centauri. At such close range, any stellar activity affects the planet almost immediately. Flares that would dissipate harmlessly across the vast distance between Earth and Sun arrive at full intensity. The travel time for radiation from Proxima Centauri to Proxima Centauri b measures only about 25 seconds. There is no warning. There is no time to prepare. When the star erupts, the planet absorbs the full force within moments. Scientists who understood Proxima Centauri's true nature raised immediate concerns about the habitability of any close-orbiting world. Their warnings were often drowned out by enthusiasm for the discovery itself. Finding a planet in the habitable zone of our nearest stellar neighbour was simply too exciting for caution to prevail in public discourse. The media preference for optimistic narratives about extraterrestrial life contributed to this imbalance. Stories about potentially habitable worlds generate more interest than stories about stellar radiation environments. Editors and producers naturally gravitated toward framings that emphasized possibility over limitation. The result was widespread public misunderstanding of what the Proxima Centauri b discovery actually implied. The disconnect between what we knew and what we communicated represented the final stage of our mischaracterization. Even after evidence accumulated showing that Proxima Centauri was actively hostile, institutional and popular understanding lagged behind. The dim, harmless neighbor star persisted in imagination long after it died in scientific fact. This lag continues today. General audiences still encounter descriptions of Proxima Centauri that emphasize its small size and low energy output, while minimizing or ignoring its violent behavior. The mischaracterization has proven remarkably persistent, surviving decades of contradictory evidence through sheer repetition and institutional inertia. Educational materials provide particularly stubborn repositories of outdated information. Textbooks written decades ago continue circulating through school systems. Planetarium shows produced before the full extent of red dwarf activity was understood still play for audiences worldwide. Wikipedia articles and popular science websites mix accurate modern information with outdated characterizations that should have been retired years ago. The scientific literature itself contains contradictory information depending on publication date and author specialty. Papers focused on exoplanet detection and characterization often adopt optimistic assumptions about stellar environments. Papers focused on stellar activity and high-energy astrophysics document hostile conditions that contradict those assumptions. Both categories of literature cite each other selectively, creating parallel narratives that rarely confront their mutual incompatibility. Understanding how we got here requires acknowledging that the error was not accidental. We chose to see Proxima Centauri as harmless because that interpretation fit our hopes and assumptions. We ignored contradictory evidence because incorporating it would have complicated our optimistic narratives about nearby habitable worlds. The psychological and sociological factors driving this selective perception deserve acknowledgement. Humans naturally seek patterns that confirm existing beliefs. Scientists, despite training in objectivity, remain susceptible to confirmation bias like everyone else. When evidence aligned with expectations, it was accepted readily. When evidence contradicted expectations, it faced heightened scrutiny that often produced rationalizations rather than revised conclusions. Institutional incentives reinforce these tendencies. Funding agencies reward discoveries more than negative results. A paper announcing a potentially habitable world attracts citations, media attention, and subsequent grant support. A paper documenting why that world probably cannot support life generates less enthusiasm despite containing equally important information. Career considerations shaped how researchers framed their findings. Early career scientists depend on visibility and citation counts for advancement. Presenting results in ways that maximize attention serves professional interests, even when more cautious interpretations would serve scientific accuracy. The competitive environment of modern academia creates pressure toward optimistic framing that accumulated across thousands of individual decisions. None of this excuses the collective failure to correctly characterize Proxima Centauri. It merely explains how intelligent, well-intentioned researchers contributed to a multi-decade pattern of misunderstanding. The error emerged not from malice or incompetence, but from entirely human tendencies operating within institutional structures that failed to correct for known biases. The star broadcast its true nature continuously. We simply chose not to listen. Proxima Centauri has always broadcast its true nature across the electromagnetic spectrum. The X-ray flares, the ultraviolet outbursts, the magnetic field configurations that drive violent activity have operated continuously since the star ignited billions of years ago. We possess the theoretical frameworks to interpret this information correctly. We developed the instrumental capabilities to detect it. We simply chose interpretations that aligned with what we wanted to believe. This pattern of selective perception extends beyond Proxima Centauri to how we approach cosmic habitability generally. We want to find life elsewhere in the universe. We want to believe that habitable worlds are common. We want our cosmic neighborhood to contain potential homes for biology. These desires shape how we interpret ambiguous evidence and frame our conclusions. The corrective does not require abandoning hope for extraterrestrial life. It requires acknowledging that honest assessment of evidence serves scientific progress better than optimistic interpretation. Understanding why Proxima Centauri cannot support life as we know it provides valuable constraints on where we should focus our search. Wishful thinking about nearby habitability wastes resources and delays genuine discovery. What comes next explores exactly what Proxima Centauri actually does to its surrounding environment. The cumulative impact of stellar activity, measured not in single dramatic events, but in the relentless accumulation of damage over time. The true nature of our closest stellar neighbor turns out to be far more hostile than even pessimistic assessments suggested. A single flare seems manageable. Energy builds in twisted magnetic field lines, reaches critical instability, and releases in a burst lasting minutes to hours. The surrounding space briefly fills with enhanced radiation before returning to baseline conditions. If flares occurred rarely enough, planetary environments might recover between events. Atmospheres could regenerate. Surface conditions could stabilize. Life could adapt. Proxima Centauri does not allow such recovery. The star produces flares at frequencies that transform occasional disruption into continuous assault. Observations spanning multiple years reveal a pattern that contradicts every assumption we made about red dwarf behavior. This is not a calm star with periodic disturbances. This is a fundamentally active star with brief intervals of reduced violence. Confirmed measurements show that Proxima Centauri produces detectable flares multiple times per day on average, not per week, not per month, per day. Some flares barely register above background noise. Others release energy equivalent to significant fractions of the star's total output over extended periods. The distribution follows a power law, with countless small events punctuated by increasingly rare but increasingly devastating major eruptions. This frequency fundamentally changes how we must think about stellar environments. A planet orbiting Proxima Centauri does not experience occasional radiation bursts separated by long calm periods. It experiences constant bombardment, varying only in intensity. The question is not whether the planet gets hit by stellar activity, but rather how severely it gets hit at any given moment. The power law distribution governing flare energies deserves careful examination. In such distributions, small events vastly outnumber large ones, but the relationship follows a predictable mathematical pattern. For every flare releasing a certain amount of energy, approximately 10 flares release 1/10 that energy. What this means practically is that Proxima Centauri produces thousands of minor flares for every major eruption. The minor events individually cause limited damage. Collectively, they maintain a constant, elevated radiation environment that never returns to true baseline. The major events punctuate this elevated baseline with catastrophic spikes that deliver concentrated damage in short intervals. Neither component alone would necessarily preclude habitability. Constant low-level radiation might be manageable for sufficiently robust biology. Occasional major events separated by long recovery periods might allow ecosystems to regenerate between blows. The combination proves devastating because it denies both the quiet conditions the simple life requires to emerge and the recovery intervals complex life requires to persist. The mathematics of cumulative exposure produce disturbing conclusions. Consider ultraviolet radiation, the wavelengths most immediately relevant to biological chemistry. Ultraviolet photons carry enough energy to break chemical bonds in organic molecules. DNA absorbs ultraviolet radiation particularly well, making this wavelength range especially dangerous to terrestrial biology. Proxima Centauri's habitable zone receives approximately 400 times more ultraviolet flux during major flare events than Earth receives from the Sun during normal conditions. This comparison understates the problem because it focuses only on peak exposure during the most extreme events. The baseline ultraviolet output between flares already substantially exceeds terrestrial levels. During the intervals between major flares, the baseline ultraviolet output still exceeds what any known Earth organism could survive without protection. Organisms on Earth's surface benefit from ozone absorption that removes most solar ultraviolet before it reaches ground level. No comparable protection exists for worlds orbiting Proxima Centauri because the very radiation that would need blocking also destroys the atmospheric constituents that might provide shielding. This ultraviolet bombardment operates continuously across timescales measured in billions of years. Proxima Centauri has maintained its current activity level since long before Earth formed. Any planet orbiting within its habitable zone has endured this radiation environment for geological epochs. The cumulative ultraviolet dose delivered over such timescales defies meaningful comparison to anything in terrestrial experience. Consider what this means for prebiotic chemistry. The origin of life on Earth required organic molecules to form, concentrate, and eventually organize into self-replicating systems. This process likely occurred in protected environments where complex chemistry could proceed without immediate destruction. Tidal pools, deep-sea vents, and subsurface aquifers have all been proposed as potential sites for life's emergence. Around Proxima Centauri, ultraviolet radiation penetrates far deeper into any aquatic environment than it does on Earth. Water provides some shielding, but the intensity of incident radiation overwhelms the protection that shallow depths provide. Only environments meters below the surface would offer comparable protection to Earth's surface conditions. The chemistry of prebiotic synthesis involves delicate molecules that ultraviolet radiation readily destroys. Amino acids, nucleotides, and lipids all absorb ultraviolet photons and undergo photochemical degradation. Building biological complexity requires these molecules to persist long enough to participate in more elaborate chemical reactions. Continuous ultraviolet bombardment prevents this persistence. Traditional habitability assessments often focus on average conditions. They calculate whether temperatures permit liquid water, whether energy input falls within acceptable ranges, whether basic chemistry could function. These assessments treat stellar radiation as a background parameter rather than an active threat. The cumulative nature of Proxima Centauri's output invalidates this approach. Average conditions mean nothing when extreme conditions occur daily and compound over billions of years. A planet might enjoy brief moments within technically habitable parameters while experiencing overall conditions that preclude any conceivable biology. But the danger was never the planet. It was always the star. X-ray emission from Proxima Centauri reveals even more extreme behavior than ultraviolet observations suggest. X-rays occupy the high-energy end of the electromagnetic spectrum, carrying photon energies thousands of times greater than visible light. These energetic photons interact destructively with matter, ionizing atoms and breaking molecular bonds through processes fundamentally different from lower-energy radiation. During quiescent periods, the star produces X-ray luminosity, comparable to the Sun's average output in this wavelength range, but delivered to planets orbiting 20 times closer. This might seem reassuring until you consider the orbital distances involved. Proxima Centauri b orbits 50 times closer to its star than Earth orbits the Sun. The inverse square law means radiation intensity increases by a factor of 2500 at this reduced distance. What appears as comparable X-ray luminosity between Proxima Centauri and the Sun translates to vastly different X-ray environments for orbiting planets. A world in Proxima's habitable zone receives thousands of times more X-ray flux than Earth receives from the Sun. Even during supposedly quiet periods, this baseline exposure already challenges the survival of complex organic chemistry. During flares, Proxima Centauri's X-ray output increases by factors of 100 or more. The most extreme events recorded sent X-ray luminosity spiking to levels that would deliver fatal radiation doses to unprotected organisms within minutes. These events are not hypothetical concerns. They have been directly measured by space-based observatories over the past 2 decades. The Chandra X-ray Observatory has monitored Proxima Centauri through multiple observation campaigns since its launch in 1999. Each campaign has detected numerous flares, with some observations capturing multiple events within single orbital periods. The XMM Newton Observatory has provided complementary data, confirming the high flare rates and extreme peak luminosities that Chandra detected. These space-based observations reveal X-ray behavior invisible to ground-based telescopes. Earth's atmosphere absorbs X-rays efficiently, preventing them from reaching surface instruments. Only by placing detectors above the atmosphere can astronomers study stellar X-ray emission directly. The investment in space-based X-ray astronomy has paid dividends in revealing the true nature of active stars like Proxima Centauri. The energy contained in X-ray photons makes them particularly dangerous to molecular structures. Unlike visible light, which interacts gently with matter through electronic excitation, X-rays ionize atoms and break chemical bonds. A single X-ray photon carries enough energy to strip electrons from multiple atoms, creating cascades of chemical damage that propagate through molecular structures. Biological molecules exposed to intense X-ray flux suffer damage that accumulates with each exposure. There is no adaptation possible. There is no building tolerance. Each X-ray photon that strikes a molecule either does damage or does not. The probabilities favor damage accumulating over time because repair mechanisms cannot operate faster than new damage arrives. Terrestrial organisms have evolved DNA repair mechanisms that correct radiation damage at rates sufficient to maintain genetic integrity under Earth's relatively benign radiation environment. These repair systems consume energy and require time to function. When damage rates exceed repair capacity, errors accumulate, mutations increase, and cellular function degrades. The X-ray flux in Proxima Centauri's habitable zone would overwhelm any conceivable biological repair mechanism. Damage would accumulate faster than any plausible chemistry could correct it. Even if life somehow emerged under these conditions, maintaining genetic fidelity across generations would prove impossible. Evolution requires inheritance, and inheritance requires information preservation that continuous X-ray bombardment prevents. 40 years of X-ray observations have documented thousands of flares from Proxima Centauri. Statistical analysis of this catalogue reveals that the star produces major X-ray flares roughly once per month and smaller, but still significant events several times per week. The cumulative X-ray dose delivered to surrounding space far exceeds anything experienced in our solar system. This flare catalogue represents only the events we happen to observe. Proxima Centauri does not pause its activity when our instruments point elsewhere. For every flare we detected, many more occurred during gaps in observational coverage. The true flare rate substantially exceeds what any finite monitoring campaign can capture. Statistical techniques allow astronomers to estimate total flare rates from incomplete observations. By analyzing the distribution of detected events and accounting for observational gaps, researchers can extrapolate to the underlying activity level. These analyses consistently indicate that Proxima Centauri flares more frequently and more intensely than direct observation alone would suggest. This pattern extends across the electromagnetic spectrum. Extreme ultraviolet emission, the wavelengths most effective at ionizing hydrogen and stripping atmospheric gases, reaches particularly devastating levels during Proxima Centauri flares. Extreme ultraviolet photons carry enough energy to ionize hydrogen atoms, the most common element in planetary atmospheres. Ionized hydrogen escapes planetary gravity more easily than neutral hydrogen, making extreme ultraviolet radiation a primary driver of atmospheric loss. Radio observations reveal energetic particle acceleration events that generate synchrotron radiation. Detecting this radiation from stellar flares indicates that particles accelerate to velocities approaching the speed of light during magnetic reconnection events. These relativistic particles constitute a radiation hazard, separate from electromagnetic emissions. Gamma-ray bursts have been detected from the most extreme flare events, indicating particle acceleration to the highest energies observable in stellar contexts. Gamma rays represent the most penetrating form of electromagnetic radiation, capable of passing through shielding that blocks lower energy photons. The detection of gamma rays from Proxima Centauri flares demonstrates that the star's violence extends to the most extreme energy scales. Each wavelength tells part of the story. Together, they describe a stellar environment of continuous violence operating across all energy scales simultaneously. There is no safe haven at any orbital distance within the star's sphere of gravitational influence. The question is merely what type of damage predominates at each location. Closer to the star, extreme ultraviolet and X-ray radiation dominate, stripping atmospheres and sterilizing surfaces. At greater distances, energetic particles become the primary concern, penetrating deeper into planetary interiors and delivering radiation doses to any potential subsurface refugia. No orbital configuration provides protection from all threats simultaneously. The temporal pattern of flare activity adds another layer of concern. Analysis of long-term observations reveals clustering behavior, with active periods producing multiple major events followed by relatively calmer intervals. This clustering means that damage does not accumulate steadily, but rather arrives in concentrated bursts. Active periods on Proxima Centauri can last for days to weeks, during which multiple significant flares occur in rapid succession. The intervals between active periods vary unpredictably from days to months. No clear periodicity emerges from the data, making prediction of active phases impossible with current understanding. This clustering behavior has profound implications for any hypothetical planetary environment. Imagine an atmosphere attempting to recover from radiation damage. Ultraviolet flux has photodissociated water molecules, freeing hydrogen that begins escaping to space. Atmospheric chemistry shifts toward a new equilibrium as remaining molecules redistribute into more stable configurations. Recovery requires time, perhaps years to decades depending on atmospheric mass and composition. Then another flare hits before recovery completes. The progress toward equilibrium reverses. Newly formed molecular species dissociate again. Hydrogen escape accelerates. The atmosphere loses more mass than it can regenerate through outgassing or other replenishment mechanisms. Then another flare hits. Then another. The clustering delivers repeated blows before any healing can occur. Each active period resets the recovery clock while adding to the cumulative damage that no amount of recovery can reverse. This prevents the gradual adaptation that might otherwise allow planetary environments to reach stable states. Every time conditions begin stabilizing, another active period disrupts the process. The star essentially keeps its surrounding space in constant disequilibrium, never allowing the quiet conditions that might permit complex chemistry to develop. The timescales involved make this disruption particularly devastating. Planetary atmospheres respond to changes over periods ranging from years to millions of years depending on the process involved. Photochemical reactions operate on timescales of seconds to days. Thermal equilibration requires months to years. Compositional evolution through atmospheric escape unfolds over millions to billions of years. Proxima Centauri's flare activity disrupts all of these timescales. Rapid photochemistry cannot proceed toward equilibrium when new flares continually restart reactions. Thermal conditions fluctuate too rapidly for stable climate patterns to emerge. Long-term atmospheric evolution faces repeated catastrophic mass loss events that outpace any replenishment mechanism. The contrast with our Sun illuminates how unusual Proxima Centauri's behavior truly is. Solar flares do occur, sometimes dramatically. The Carrington event of 1859 produced aurora visible at tropical latitudes and disrupted telegraph systems worldwide. Charged particles from this solar storm induced electrical currents in telegraph wires, strong enough to shock operators and set fire to telegraph paper. A similar event today would cause significant infrastructure damage. Satellite electronics would face radiation exposure exceeding design tolerances. Power grid transformers might fail due to induced currents. Communication systems relying on ionospheric propagation would experience disruption lasting days to weeks. Economic losses could reach trillions of dollars depending on event severity and response effectiveness. But solar superflares of Carrington magnitude occur perhaps once or twice per century. The intervals between major events span human generations. Earth's magnetic field and atmosphere have decades to centuries between significant solar events to maintain their protective functions. Recovery and repair proceed faster than new damage accumulates. Proxima Centauri produces events comparable to the Carrington event multiple times per year. Larger events exceeding anything in recorded solar history occur every few years. The most extreme flares release energies that dwarf the Carrington event by factors of thousands. The star has delivered billions of these blows to surrounding space since it ignited nearly 5 billion years ago. The cumulative energy released through flares over Proxima Centauri's lifetime exceeds comprehension. Consider that a single major flare might release energy equivalent to billions of nuclear weapons detonating simultaneously. The star produces dozens of such events every year. Multiply by billions of years. The total energy delivered to surrounding space through flare activity alone exceeds the energy contained in all fossil fuels ever extracted from Earth by factors beyond meaningful calculation. This energy does not disappear. It interacts with whatever matter exists within range. Photons ionize atoms. Particles collide with molecules. Energy transforms into chemical damage, atmospheric heating, and mass loss. The cumulative effect of billions of years of such processing transforms any planetary environment into something fundamentally different from its original state. What we misunderstood was the source of danger in stellar environments. We assumed that small, dim stars posed less threat because they contained less total energy. This reasoning overlooked how that energy gets released. A star can contain less total energy while releasing far more of it through violent activity. The ratio of flare energy to total stellar luminosity matters more than absolute luminosity alone. Proxima Centauri has a total luminosity only about 1/6 of 1% that of the Sun. But the star releases a far larger fraction of this energy through flares. While the Sun releases perhaps 1/10,000th of its energy through flare activity over long timescales, Proxima Centauri releases a substantially larger fraction through magnetic reconnection events. By this measure, Proxima Centauri ranks among the most dangerous stellar environments in the galaxy. The star releases a larger fraction of its total energy through flares than the Sun does. This fractional activity, applied over billions of years, transforms surrounding space into a radiation bath that no known chemistry could survive. The stellar physics driving this behavior operates continuously, regardless of whether we observe it. When we turn our telescopes away from Proxima Centauri, the star does not stop flaring. When instruments malfunction or observations get cancelled, the radiation output continues unabated. Our limited monitoring has captured only fragments of a process that has operated without pause for epochs. Consider the implications of observational incompleteness. We have monitored Proxima Centauri intensively for perhaps 20 years using modern space-based instruments. The star has been actively flaring for approximately 4.85 billion years. Our observations sample roughly 4 billionths of the star's active history. Extrapolating from such limited data, requires confidence in statistical methods that assume the observed sample represents typical behavior. If Proxima Centauri's current activity level approximates its historical average, our extrapolations provide meaningful estimates of cumulative flare effects. If the star has varied significantly over its lifetime, our estimates might substantially understate or overstate historical activity. Fortunately, stellar physics provides constraints on long-term behavior. The convective mixing that drives magnetic activity operates continuously as long as the star burns hydrogen. There is no reason to expect dramatic variations in average activity level over the star's main sequence lifetime. If anything, theoretical models suggest that red dwarf activity might increase slightly as these stars age and slowly contract. The contraction would strengthen internal motions and potentially intensify magnetic field generation. The Proxima Centauri we observe today might be slightly less active than it was billions of years ago, or slightly more active than it will be billions of years hence. Either way, the fundamental pattern of continuous violent flaring has persisted throughout the star's existence. Long-term monitoring programs are gradually filling the gaps in our knowledge. The Everscope project has tracked Proxima Centauri continuously for years, capturing flare events that previous sporadic observations missed. This array of small telescopes monitors the entire accessible sky simultaneously, ensuring that transient events do not escape detection due to pointing limitations. The Everscope data revealed that Proxima Centauri flares even more frequently than previous estimates suggested. Events that would have been missed by targeted observation campaigns showed up in the continuous monitoring stream. The baseline flare rate required upward revision as more complete data became available. Space-based monitoring by missions including the Transiting Exoplanet Survey satellite has added complementary data. TESS observes large portions of the sky continuously for weeks at a time, detecting brightness variations with precision exceeding ground-based capabilities. Proxima Centauri appeared in TESS observation sectors, contributing additional flare detections to the growing catalogue. Each additional observation strengthens our understanding of just how active this star truly is. The trend consistently points toward higher activity levels than earlier estimates assumed. Every improvement in observational coverage reveals more flares, not fewer. The star keeps proving itself more violent than previous data suggested. The picture that emerges from comprehensive monitoring looks nothing like the quiet red dwarf we once imagined. Proxima Centauri is one of the most actively flaring stars in the solar neighborhood. Its position as our nearest stellar neighbor means we receive more detailed information about its behavior than any comparable red dwarf. What we see is not reassuring. 2019 brought perhaps the most dramatic single observation of Proxima Centauri's potential for violence. Astronomers detected a superflare that briefly increased the star's brightness in ultraviolet wavelengths by a factor of 14,000. This single event lasted only 7 seconds at peak intensity, but delivered more ultraviolet energy than the star produces during hours of normal operation. The detection came from a coordinated multi-wavelength observation campaign designed specifically to characterize Proxima Centauri's flare behavior. 5 ground-based telescopes and 2 space-based instruments monitored the star simultaneously across wavelengths from radio to X-ray. This comprehensive coverage ensured that the superflare was characterized across the entire electromagnetic spectrum. 14,000 times baseline brightness. The number requires contemplation to appreciate its significance. Imagine standing in dim candlelight when suddenly the illumination increases to stadium floodlight intensity. Now, increase that ratio by another factor of 10. That approximates what the 2019 superflare represented relative to Proxima Centauri's normal output. 7 seconds of exposure at close orbital range would have delivered radiation doses exceeding anything Earth organisms have ever experienced from our Sun. The total ultraviolet energy released during those 7 seconds would take hours to accumulate during quiescent conditions. Any hypothetical life on Proxima Centauri b would have faced this onslaught without warning, without protection, and without the possibility of adaptation. the event's duration matters as much as its intensity. 7 seconds provides no time for any conceivable biological or chemical response. Atmospheric shielding cannot adjust on such timescales. Organisms cannot seek shelter. Chemical equilibria cannot shift to minimize damage. The full force of the radiation arrives and departs before any protective mechanism could engage. The 2019 superflare was not unique. It was merely the largest event captured during a particular monitoring campaign. Statistical analysis suggests that events of comparable or greater magnitude occur regularly over timescales of years to decades. Earlier observations had detected major flares from Proxima Centauri, but none quite reached the 2019 event's intensity. This does not mean such intense flares were absent before 2019. It means our observations happened to capture an exceptional event during a period of particularly comprehensive monitoring. Similar or larger events almost certainly occurred during the billions of years before human observers turned their instruments toward this star. The statistical distribution of flare energies provides insight into unobserved events. Power law distributions extend to arbitrarily high energies, limited only by the physical processes generating them. The maximum flare energy Proxima Centauri can produce depends on how much magnetic energy the star can store before releasing it through reconnection. Theoretical calculations suggest that red dwarfs can produce superflares substantially larger than any yet observed from Proxima Centauri. The magnetic field configurations necessary for such events require time to build, making them rare. But rare does not mean impossible. Over billions of years, even events occurring once per million years happen thousands of times. Cumulative damage from this flare history cannot be undone. Whatever atmospheric or surface conditions might have once existed on planets orbiting Proxima Centauri have been processed through billions of years of radiation exposure. The star has had more than enough time to strip, sterilize, and transform any world within its reach. Atmospheric loss operates as a one-way process for most planetary configurations. Once gas escapes to space, recovering it requires ongoing outgassing from planetary interiors or delivery through cometary impacts. These replenishment mechanisms operate slowly compared to the loss rates that Proxima Centauri's radiation drives. The atmospheric budget runs perpetually negative under such conditions. Surface sterilization proceeds even faster than atmospheric stripping. Any biological material that emerged would need to develop radiation resistance, exceeding anything known in terrestrial organisms, then maintain that resistance across generations while facing continuous radiation pressure. This cumulative processing distinguishes red dwarf environments from the relatively gentle conditions around Sun-like stars. Our Sun certainly poses dangers to nearby worlds. Mercury has no atmosphere, partly due to solar radiation and wind stripping it away. Venus demonstrates what happens when greenhouse warming runs away under intense stellar heating. Mars shows how smaller worlds lose their atmospheres over geological time, even under moderate stellar conditions. But the danger from our Sun arrives in measured doses separated by recovery intervals. Major solar events occur rarely enough that planetary systems can equilibrate between disturbances. The relatively calm intervals lasting decades to centuries allow complex chemistry to proceed and biological evolution to operate. Earth has maintained a stable biosphere for billions of years, despite orbiting an active star. Proxima Centauri's danger arrives continuously, compounds relentlessly, and never permits equilibration. The star actively prevents the conditions that allowed life to flourish on Earth. Each flare contributes to ongoing damage. Each year adds to the cumulative toll. Each billion years ensures that nothing survives in recognizable form. The distinction matters profoundly for any consideration of habitability. Life, as we understand it, requires stable chemistry, operating over extended timescales. Biological evolution demands environments that remain consistent enough for natural selection to function. Ecosystems need conditions that allow complex webs of interaction to develop and persist. Proxima Centauri's cumulative assault prevents all of this. the star actively destroys the conditions that might otherwise permit biological complexity. Even if some robust form of life could theoretically survive individual flare events, the cumulative damage over geological timescales would preclude the evolutionary development of complexity. Simple organisms might conceivably persist in protected niches, though even this seems unlikely, given the penetrating nature of the highest energy radiation. Complex multicellular life requiring stable environments over millions of years has no plausible pathway to emergence around such active stars. We spent decades looking for habitable worlds around our nearest stellar neighbour without fully acknowledging what that neighbour was doing to surrounding space. The mischaracterization was not merely academic. It shaped research priorities, funding decisions, and public understanding of cosmic habitability. Resources devoted to characterizing potential habitability around Proxima Centauri might have been better spent on more promising stellar targets. Public expectations raised by optimistic announcements will face eventual disappointment as the full picture of red dwarf hostility becomes widely understood. The lag between scientific knowledge and public perception creates confusion that serves neither science communication nor public trust. What comes next examines another dimension of Proxima Centauri's hostility. The flares that dominate discussion actually represent only the most visible component of stellar assault. Between and beneath the dramatic events operates a continuous process of erosion through stellar wind and particle flux. This invisible pressure works constantly, requiring no dramatic events to accomplish its destructive purpose. Between flares, Proxima Centauri appears calm. The visible light output stabilizes. The X-ray emission drops to baseline levels. An observer, checking occasionally, might conclude that the star spends most of its time in quiet states, punctuated by occasional disturbances. This conclusion would be catastrophically wrong. The intervals between flares do not represent periods of safety. They represent periods when destruction operates through different mechanisms. Stellar wind, particle flux, and baseline radiation output continue regardless of flare activity. These processes work slowly enough that individual observations cannot detect their effects. They work continuously enough that nothing escapes their influence. The previous section documented the dramatic violence of Proxima Centauri's flare activity. But focusing exclusively on flares creates a dangerous illusion. It suggests that the time between flares might provide refuge, recovery, or stability. No such refuge exists. Stellar wind emerges from the outer atmosphere of every star, including our own Sun. Charged particles accelerate outward along magnetic field lines, creating a constant flow of material into surrounding space. The Sun produces solar wind that shapes planetary magnetospheres and creates the conditions for aurora on Earth. At our distance from the Sun, solar wind pressure remains manageable. Earth's magnetic field deflects most particles harmlessly into radiation belts, or guides them toward polar regions where they produce beautiful but benign light displays. The solar wind represents a continuous but gentle pressure against Earth's magnetic shield. Approximately 400 kilometers per second of protons and electrons stream past our planet constantly. This flow carries about 1 million tons of material away from the Sun every second. Despite these impressive numbers, the actual pressure exerted on Earth's magnetosphere remains modest enough that our planet has maintained its atmosphere for billions of years. Proxima Centauri produces stellar wind that dwarfs solar wind intensity at comparable distances. The star's fully convective interior and powerful magnetic dynamo accelerate particles to higher speeds and densities than the Sun achieves. This enhanced stellar wind flows continuously outward, impacting anything in its path with force that would reshape any planetary environment over geological timescales. The physics driving enhanced stellar wind from red dwarfs connects directly to the magnetic field generation that produces flares. The same turbulent dynamo that creates tangled magnetic loops also accelerates particles along magnetic field lines with greater efficiency than the organized solar dynamo achieves. Strong magnetic fields covering large fractions of the stellar surface provide abundant pathways for particle acceleration. Measurements of Proxima Centauri's stellar wind rely on indirect techniques, since we cannot send spacecraft to sample it directly. The nearest human-made object, Voyager 1, required over 40 years to reach the edge of our own solar wind environment. Reaching Proxima Centauri's stellar wind would require journey times measured in tens of thousands of years using current propulsion technology. Instead, astronomers study stellar wind through its interactions with surrounding material. Observations of how stellar wind encounters the interstellar medium create detectable signatures in radio wavelengths. Theoretical models of red dwarf physics constrain the range of plausible wind properties based on stellar mass, rotation rate, and magnetic field strength. Spectroscopic observations of stellar atmospheres reveal the conditions from which wind particles accelerate. These indirect approaches suggest wind pressures exceeding solar values by factors ranging from dozens to hundreds, depending on stellar activity phase. The uncertainty in these estimates spans nearly an order of magnitude. We cannot yet precisely characterize Proxima Centauri's stellar wind environment with the confidence we bring to solar wind measurements made by spacecraft instruments. What we know with confidence is that the wind pressure substantially exceeds what Earth experiences and arrives at planetary orbital distances much closer to the source. The inverse square law governs how wind pressure decreases with distance. Proxima Centauri b orbits approximately 20 times closer to its star than Earth orbits the Sun. Even if the wind emerged with identical properties to solar wind, the pressure at Proxima b's orbital distance would exceed Earth's experience by a factor of 2500. Combined with the enhanced wind production from Proxima Centauri's active magnetic dynamo, the actual pressure differential likely exceeds factors of 10,000 or more. This represents not a gentle breeze, but a constant hurricane of charged particles impacting any world unfortunate enough to orbit within range. For a world like Proxima Centauri b, orbiting at 7.5 million kilometers, stellar wind pressure represents a constant force pushing against any atmospheric envelope. The pressure operates in one direction only, outward from the star. Unlike gravitational forces that pull equally from all directions, stellar wind creates asymmetric stress that any atmosphere must resist continuously. Without an exceptionally strong planetary magnetic field, this pressure gradually erodes atmospheric gases into space. The erosion operates continuously over timescales measured in millions and billions of years. Each second removes a small amount of atmospheric material. Each year removes slightly more. Each billion years removes quantities that transform planetary environments from potentially habitable to definitively sterile. It wasn't hidden. It was overlooked. The scientific community's focus on dramatic flare events obscured the importance of continuous processes operating between those events. A single superflare makes headlines. Decades of steady atmospheric erosion generates no press releases. Yet the cumulative effect of continuous erosion may exceed the impact of even the most dramatic individual events. Atmospheric escape represents one of the least appreciated threats to planetary habitability. The concept seems simple enough. Gas molecules in a planetary atmosphere move at speeds determined by temperature. Some molecules in the high-velocity tail of the distribution move fast enough to escape the planet's gravitational pull. Given enough time, atmospheric loss through this thermal escape process can substantially alter planetary conditions. On Earth, atmospheric gases occasionally gain enough energy to escape our planet's gravitational pull. Hydrogen, the lightest element, escapes most easily. Heavier gases like nitrogen and oxygen require higher velocities to escape, making their loss rates correspondingly lower. This escape happens at rates slow enough that volcanic outgassing and other processes replenish lost material. Our atmosphere maintains roughly constant composition over geological time, through a balance between loss and replenishment. Around Proxima Centauri, the escape calculus changes dramatically. Enhanced stellar wind pressure drives atmospheric loss at rates that outpace any plausible replenishment mechanism. The closer orbital distance means particles arrive with more energy and apply greater force. The frequent flares temporarily accelerate escape rates by orders of magnitude during active periods. But even between flares, the baseline escape rate far exceeds anything experienced in our solar system. Multiple escape mechanisms operate simultaneously around active red dwarfs. Thermal escape accelerates because extreme ultraviolet radiation heats upper atmospheric layers to temperatures far exceeding anything in Earth's thermosphere. This heating expands the atmosphere outward, placing more material at altitudes where stellar wind can strip it away directly. Hydrodynamic escape occurs when heating becomes so intense that the upper atmosphere flows outward as a bulk fluid rather than escaping molecule by molecule. This process can remove atmospheric material orders of magnitude faster than thermal escape alone. Models suggest that hydrodynamic escape operates continuously around close-in planets orbiting active red dwarfs. Ion pickup occurs when stellar wind particles collide with atmospheric molecules and ionize them. The newly charged particles then follow magnetic field lines that carry them away from the planet entirely. This process bypasses the gravitational barrier that limits thermal escape, allowing even heavy molecules to be removed efficiently. Sputtering happens when energetic stellar wind particles impact atmospheric molecules with enough force to knock them out of the atmosphere directly. The cumulative effect of billions of collisions per second over billions of years removes quantities of material that no planetary atmosphere could survive. These mechanisms operate simultaneously and reinforce each other's effects. High ultraviolet flux heats and expands the atmosphere into regions where stellar wind pressure is strongest. The expanded atmosphere presents a larger target for ion pickup and sputtering processes. Flare events that enhance both radiation and particle flux create temporary conditions of catastrophic loss. The baseline conditions between flares permit steady erosion that compounds over time without interruption. Theoretical models of atmospheric evolution around Proxima Centauri suggest that Earth-like atmospheres could not survive for geologically significant periods. A world starting with Earth's atmospheric composition would lose its air over timescales of hundreds of millions of years. This might seem like a long time from a human perspective, but it represents only a few % of the time since Proxima Centauri formed. Any world that formed with Proxima Centauri b's characteristics has had billions of years to experience this loss. Even if the planet began with an atmosphere 10 times more massive than Earth's, continuous erosion over 4 billion years would have stripped it entirely. The mathematics of exponential loss ensures that no reasonable initial atmospheric mass survives the timescales involved. The mathematics of atmospheric escape involve complex interactions between stellar radiation, stellar wind, planetary magnetic fields, and atmospheric chemistry. No single factor determines outcomes. Computer models must track energy deposition from multiple radiation sources, chemical reactions that alter atmospheric composition, magnetic field configurations that either protect or expose atmospheric material, and gravitational forces that vary with altitude. The combination of factors around Proxima Centauri uniformly favors rapid atmospheric depletion. Every variable that can be adjusted within physically plausible ranges points toward the same conclusion. Atmospheres do not survive around close-in planets, orbiting active red dwarfs. The absence of a strong protective magnetic field around Proxima Centauri b remains unknown, but profoundly important. Earth's magnetic field deflects most stellar wind particles before they reach our atmosphere. The magnetosphere extends tens of thousands of kilometers sunward, creating a protective bubble within which our atmosphere persists relatively unmolested. This deflection reduces both direct atmospheric stripping and the chemical alterations that charged particles would otherwise cause. Solar wind particles that do penetrate the magnetosphere arrive in polar regions where magnetic field lines converge. The famous aurora borealis and australis mark the locations where this limited particle precipitation occurs. The rest of the atmosphere remains shielded from direct particle bombardment. Proxima Centauri b orbits so close to its star that tidal forces have almost certainly synchronized its rotation with its orbital period. One face permanently points toward the star, while the other faces eternal darkness. This gravitational locking is the same phenomenon that keeps one face of our moon always pointing toward Earth. The tidal forces responsible for this synchronization operate more strongly at closer orbital distances and have had billions of years to complete their work. Synchronous rotation probably prevents the planet from generating a strong internal dynamo through differential rotation. Earth's magnetic field arises from convective motions in our planet's liquid iron outer core. These motions are driven partly by Earth's rotation, which creates Coriolis forces that organize convective cells into patterns conducive to magnetic field generation. A synchronously rotating planet spins much more slowly relative to its orbital period. Proxima Centauri b completes one rotation every 11.2 days rather than every 24 hours like Earth. This slower rotation generates weaker Coriolis forces and less organized convective patterns. The resulting magnetic field, if any exists, would be substantially weaker than Earth's. Without a robust magnetic field, Proxima Centauri b directly exposes whatever atmosphere it possesses to stellar wind bombardment. The wind particles do not deflect around a protective magnetosphere. They impact atmospheric molecules directly at whatever velocity they carried from the star. Each collision transfers energy and momentum to atmospheric molecules. The cumulative effect over billions of years strips away any gas that might have existed. Even if some atmosphere survives direct erosion through stellar wind, the chemistry of that atmosphere would be transformed beyond recognition. Charged particles splitting molecular bonds would convert stable atmospheric gases into reactive species. Molecular nitrogen, the dominant component of Earth's atmosphere, would be dissociated into atomic nitrogen that escapes more easily or reacts with other species. Any oxygen or ozone layer would face constant destruction through photochemistry and particle impact. Ozone forms on Earth when ultraviolet radiation splits oxygen molecules into atoms that then combine with other oxygen molecules. This same radiation also destroys ozone molecules, establishing a dynamic equilibrium that maintains Earth's protective ozone layer. Around Proxima Centauri, the extreme ultraviolet flux would destroy ozone molecules far faster than photochemistry could produce them. No stable ozone layer could exist even if free oxygen were present in the atmosphere. The chemistry that permits life on Earth would face constant disruption without possibility of establishing the equilibrium conditions that biological processes require. This brings us back to the star itself and what its continuous output means for surrounding space. The particle flux from Proxima Centauri extends far beyond the stellar wind proper. While stellar wind consists primarily of thermal particles accelerated through normal atmospheric expansion, flare activity produces populations of much higher energy particles through different acceleration mechanisms. Magnetic reconnection events accelerate particles to relativistic velocities through processes that convert magnetic field energy directly into particle kinetic energy. These high-energy particles travel at speeds approaching the speed of light, carrying energies thousands to millions of times greater than typical stellar wind particles. On Earth, we call such energetic particles cosmic rays, regardless of their source. Galactic cosmic rays arrive from distant supernova remnants, where shock waves have accelerated particles over millions of years. Solar energetic particles arrive during major solar flare events, though these rarely reach the energies that galactic sources achieve. Proxima Centauri's frequent flaring produces cosmic ray populations that arrive continuously rather than during rare events. The star accelerates particles to galactic cosmic ray energies multiple times per day during active periods. Even during nominally quiet phases, lower-level magnetic activity produces elevated particle fluxes that exceed anything Earth experiences from solar sources. Cosmic ray flux from Proxima Centauri substantially exceeds what Earth experiences from all sources combined. Our planet receives galactic cosmic rays at rates modulated by the solar magnetic field, which partially shields the inner solar system from external particle populations. The Sun contributes relatively few high-energy particles to Earth's cosmic ray environment, because solar particle events rarely reach the energies that galactic sources achieve. Proxima Centauri's frequent flaring accelerates particles to energies comparable to galactic cosmic rays, but delivers them at much higher intensities due to proximity. A supernova remnant producing cosmic rays lies thousands of light-years away. Proxima Centauri lies 4 light-years away. A world orbiting within the habitable zone lies less than 1 light-minute from the source. The intensity difference that proximity creates is staggering. Cosmic ray flux decreases with the square of distance from the source. A particle source 1,000 times closer delivers 1 million times more particles to any target. The combination of frequent particle acceleration events and extreme proximity creates radiation environments that would be lethal to most Earth organisms, even without considering other radiation threats. High-energy particles penetrate shielding that blocks lower-energy radiation. Visible light stops at any opaque surface. Ultraviolet radiation penetrates a few millimeters into skin or water. X-rays penetrate further, but are absorbed by dense materials like lead or concrete. Cosmic ray particles penetrate through meters of rock, through any biological tissue, through any protective structure that might conceivably exist. The particles do not stop until they interact with matter through nuclear processes that create secondary radiation cascades. When a high-energy cosmic ray strikes an atomic nucleus, the collision produces showers of secondary particles that spread the radiation dose through surrounding material. These secondary particles include neutrons, which penetrate even further than the original cosmic ray before depositing their energy. This penetrating radiation ensures that no surface location and few subsurface locations around Proxima Centauri would provide safe environments for biological processes. Organisms on a planetary surface would receive direct cosmic ray exposure. Organisms in caves or underwater would receive secondary radiation from particle showers initiated above them. Even organisms evolved to tolerate radiation would face doses exceeding their survival limits. The most radiation-resistant organism known on Earth, Deinococcus radiodurans, can survive acute doses of several thousand Gray. The continuous cosmic ray flux in Proxima Centauri's habitable zone delivers doses exceeding this tolerance threshold over timescales of years to decades. No conceivable biological adaptation provides protection against such sustained exposure. Even organisms shielded by kilometers of rock would experience elevated radiation from secondary particles. The cosmic ray flux at Proxima Centauri's habitable zone is high enough that secondary radiation penetrates to depths that would be safe in Earth's environment. There is no available refuge that combines access to energy sources necessary for life with protection from radiation damage. The combination of stellar wind pressure, cosmic ray flux, and electromagnetic radiation creates an environment fundamentally incompatible with chemistry as we understand it. Complex molecules that form under these conditions face rapid destruction through multiple pathways operating simultaneously. Any molecular complexity that might emerge by chance gets erased before it can build toward biological organization. Prebiotic chemistry requires molecules to persist long enough to participate in increasingly complex reactions. Simple molecules must combine into amino acids. Amino acids must link into peptides. Peptides must fold into functional proteins. Each step requires the products of previous steps to survive long enough for further reactions to occur. Around Proxima Centauri, radiation destroys complex molecules faster than any plausible synthesis pathway can produce them. The steady-state molecular complexity, achievable under such conditions, cannot support biology. Life requires building complexity over time through iterated chemical reactions. Continuous destruction prevents this accumulation, regardless of how efficiently synthesis proceeds. Variability adds another dimension to this hostility. Proxima Centauri does not maintain constant output, even during nominally quiet periods. The star's magnetic field configuration changes continuously as convective motions stir its interior. Surface features evolve on timescales of days to weeks. The stellar output fluctuates in response to these internal changes, even when no major flares occur. This variability means that no orbital configuration provides consistent conditions. A planet cannot simply establish equilibrium with average stellar output because that average masks substantial variation. What works during quiet phases fails during active periods. What survives active periods may not persist through the following quiet phase. The Sun exhibits its own variability through the roughly 11-year solar cycle. Solar activity waxes and wanes as magnetic field patterns build and release. Earth experiences this cycle as modest changes in total irradiance, approximately 0.1% variation, and occasional increases in flare frequency. The variations remain small enough that terrestrial climate and biology adjust without fundamental disruption. Some research has connected solar cycle variations to minor climate fluctuations on Earth. The Maunder minimum, a period of reduced solar activity from 1645 to 1715, coincided with particularly cold temperatures in Europe and North America. But even this pronounced solar minimum produced climate effects measured in fractions of a degree, not the catastrophic variations that would prevent biological adaptation. Proxima Centauri's variability dwarfs solar variations by every measurable standard. The star does not follow neat periodic cycles. Activity fluctuates chaotically, driven by the turbulent convection that dominates its interior. The solar cycle emerges from organized magnetic field evolution within the Sun's convective zone. Magnetic flux tubes rise through the convective zone, emerge through the surface as sunspots, and eventually disperse as the solar dynamo reverses polarity. This organized process produces predictable cycle lengths, averaging 11 years with variations of a few years around that average. Proxima Centauri's fully convective interior lacks the tachocline boundary layer where the solar dynamo operates. Magnetic field generation occurs throughout the stellar volume, through turbulent processes that resist simple characterization. The resulting activity pattern appears essentially random when analyzed statistically, showing no significant periodic components that would enable prediction. This chaotic variability prevents any stabilization of nearby environments. Planetary climates cannot settle into equilibrium states because the forcing function changes unpredictably. Atmospheric chemistry cannot establish stable cycles because the radiation input fluctuates too rapidly and irregularly. Any temporary equilibrium gets disrupted before it can persist long enough to enable biological adaptation. Decades of observation have revealed just how unstable Proxima Centauri's output truly is. Year-to-year variations in flare rate exceed factors of several. Some years produce major flares weekly, while other years show months between significant events. Month-to-month changes in baseline X-ray emission can double or halve depending on stellar magnetic configuration. Day-to-day fluctuations in ultraviolet output create conditions that no single measurement can adequately characterize. The scientific community initially attributed this variability to observational limitations rather than stellar physics. Instruments have noise. Weather interferes with ground-based observations. Scheduling conflicts create gaps in monitoring coverage. Poor data seemed more plausible than genuinely chaotic stellar behavior. As monitoring improved and data accumulated, the chaotic nature of Proxima Centauri's output became undeniable. Better instruments showed the same variability patterns. Space-based observations eliminated weather as an explanation. Continuous monitoring campaigns confirmed that gaps in coverage were not hiding regular patterns. The variability is real, intrinsic to the star, and beyond any current ability to predict. This chaos operates on top of already hostile baseline conditions. Even if Proxima Centauri maintained perfectly constant output at its average level, that average would still preclude habitability. The ultraviolet flux would still destroy organic molecules. The stellar wind would still erode atmospheres. The cosmic ray flux would still deliver lethal radiation doses. The variability adds insult to injury, ensuring that even temporary refuges from stellar violence cannot persist long enough to matter. Understanding this invisible erosion required moving beyond event-focused thinking. Brightness increases by factors of thousands. X-ray emission spikes by orders of magnitude. These changes appear clearly in data and generate publishable results quickly. The continuous processes operating between flares require sustained monitoring and sophisticated analysis to detect. Measuring stellar wind properties requires accumulating data over years to decades. Characterizing cosmic ray environments requires statistical analysis of particle detection events. Quantifying baseline radiation requires separating constant components from variable backgrounds. Scientific culture tends to reward discoveries of discrete phenomena over characterization of continuous processes. A paper announcing a dramatic flare event gets citations and attention. A paper documenting baseline stellar wind properties attracts less interest despite potentially greater importance for understanding habitability. This incentive structure delayed recognition of just how hostile Proxima Centauri's continuous output truly is. The full picture emerges only when combining flare observations with stellar wind measurements, with cosmic ray flux estimates, with baseline radiation characterization. Each component tells part of the story. Together, they describe an environment where destruction operates continuously through multiple channels simultaneously. No single observation reveals this comprehensive hostility. The star appears manageable when viewed through any single lens. A study focused solely on visible light might conclude that Proxima Centauri provides stable illumination suitable for photosynthesis. A study focused solely on average temperatures might conclude that liquid water could exist in the habitable zone. Only by integrating across wavelengths, timescales, and physical processes does the true nature of Proxima Centauri become apparent. This integration happened slowly over decades of research. Different scientific communities studied different aspects of red dwarf behavior without always communicating their findings effectively. The stellar wind experts knew their piece of the puzzle. The X-ray astronomers knew theirs. The planetary scientists operated with incomplete information from both groups while developing habitability assessments that assumed benign stellar conditions. What emerges from proper integration is a picture of systematic environmental destruction operating at every conceivable scale. Proxima Centauri does not merely threaten nearby worlds through occasional violent outbursts. It actively processes them through continuous erosion that operates regardless of flare activity. The quiet periods are not safe. They are merely periods when destruction proceeds through different channels at different rates. The next section brings together everything we have learned about Proxima Centauri's true nature. The danger was never hidden in some subtle signal, awaiting future discovery. It was always present in the data we collected and the physics we understood. We simply failed to see what was in front of us because we wanted to believe our nearest stellar neighbour might be friendly. The final resolution of this mischaracterization requires acknowledging that we deceived ourselves, and that this self-deception extends far beyond a single star to encompass billions of similar objects throughout our galaxy. The evidence was always there. From the moment Robert Innes identified Proxima Centauri in 1915, the data contained signals that should have warned us about this star's true nature. We missed those signals not because they were subtle, but because we were not prepared to see them. Every observation of Proxima Centauri fit into a framework that assumed small, dim stars posed minimal danger. When observations contradicted that framework, we adjusted the observations rather than the framework. When data accumulated that made the framework untenable, we compartmentalized the knowledge rather than changing our fundamental assumptions. This is not a story about recent discovery revealing ancient secrets. This is a story about decades of self-deception enabled by wishful thinking and institutional inertia. The hostile nature of Proxima Centauri has been scientifically documented for half a century. We simply chose not to integrate that documentation into our broader understanding of stellar environments. The timeline of accumulating evidence makes this failure particularly stark. By the 1970s, astronomers had detected frequent flaring from Proxima Centauri that exceeded anything observed from comparable stars. By the 1980s, ultraviolet observations revealed baseline radiation levels incompatible with surface habitability. By the 1990s, X-ray satellites documented activity patterns that should have ended speculation about benign stellar conditions. Each decade brought new evidence. Each decade saw that evidence minimized, compartmentalized, or explained away. The scientific community developed an elaborate apparatus of rationalization that allowed continued optimism despite accumulating contradictions. The mischaracterization began with projecting solar behavior onto a fundamentally different type of star. It continued through selective attention to observations that confirmed our hopes while minimizing those that challenged them. It persists today in popular descriptions that emphasize Proxima Centauri's dimness while ignoring its violence. But what we misunderstood was the source of danger, and that misunderstanding extends far beyond our closest stellar neighbor. Proxima Centauri is not unusual among red dwarfs. The flare activity, stellar wind intensity, and radiation output that characterize this star appear throughout the population of small, cool stars. Every red dwarf we have studied in comparable detail shows similar behavioral patterns. The violence is not exceptional. It is definitional. This universality emerged gradually from surveys of nearby red dwarfs. Barnard's star, the second closest stellar system to Earth, shows comparable activity levels when monitored with sufficient sensitivity. Wolf 359, Lalande 21-185, Ross 128. Each star examined closely enough reveals the same fundamental hostility that Proxima Centauri displays. The pattern holds across variations in stellar mass, age, and rotation rate. Younger red dwarfs flare more intensely than older ones, but even ancient red dwarfs maintain activity levels that would sterilize nearby planetary surfaces. Faster rotating red dwarfs show enhanced magnetic activity, but even slowly rotating examples produce radiation environments incompatible with biology as we understand it. No red dwarf studied to date provides the calm, stable environment that life apparently requires. The search for exceptions continues, but each new observation confirms the rule rather than breaking it. Red dwarfs are hostile by nature, not by circumstance. Red dwarfs constitute approximately 70% of all stars in our galaxy. These small, cool objects outnumber Sun-like stars by ratios exceeding 10-1. The Milky Way contains roughly 400 billion stars, of which approximately 280 billion are red dwarfs. This numerical dominance shapes every statistical estimate of planetary populations and potential habitability. When scientists calculate the number of potentially habitable planets in the Milky Way, red dwarf systems dominate the statistics simply because red dwarfs dominate stellar populations. Early estimates suggested that tens of billions of Earth-sized planets might orbit within red dwarf habitable zones. These estimates fueled optimism about the prevalence of life in our galaxy. This numerical dominance made optimism about red dwarf habitability particularly appealing. If small stars could host living worlds, then the galaxy might contain billions of inhabited planets. The universe would be teeming with life. The Fermi paradox would become even more puzzling because technological civilizations should be everywhere. The recognition that red dwarfs are uniformly hostile fundamentally changes this calculation. Those billions of potentially habitable worlds around small, cool stars may not be habitable at all. The planets exist. The orbital distances place them within nominal habitable zones. The water might flow under the right circumstances, but the stellar environments prevent the stability that life requires to emerge and persist. Subtracting red dwarf systems from habitability estimates reduces the number of potentially life-bearing worlds by roughly an order of magnitude. Instead of tens of billions of candidates, we face perhaps a few billion at most. Instead of habitable worlds being common throughout the galaxy, they become rare exceptions concentrated around unusual stellar types. This reassessment represents one of the most significant revisions in our understanding of cosmic habitability. Decades of optimistic speculation about red dwarf planets must now be qualified with acknowledgement of stellar hostility. The habitable zone concept itself requires modification when applied to stars that actively destroy habitability through radiation and particle flux. The traditional habitable zone considers only temperature. It asks where liquid water could exist on a planetary surface, given the star's luminosity and the planet's atmospheric properties. This thermal definition remains useful for initial screening of planetary candidates, but it tells us nothing about whether the stellar radiation environment permits the chemistry that life requires. A more complete habitability assessment must consider stellar activity alongside thermal conditions. A planet might sit perfectly within the temperature-based habitable zone while receiving radiation doses that preclude biology. The nominal habitable zone and the actual habitable zone may not overlap at all around active stars. For red dwarfs, this mismatch appears universal. The temperature-based habitable zone lies close to the star where radiation intensity is highest. The actual habitable zone, if it exists at all, would need to lie far beyond the orbital distances where liquid water can exist. No orbital configuration satisfies both thermal and radiation requirements simultaneously. Scientists have proposed various mechanisms that might allow life to survive around red dwarfs despite stellar activity. Each proposal represents an attempt to salvage habitability, estimates that institutional momentum and career investments have made difficult to abandon. Each proposal deserves examination against the evidence we have accumulated. Planetary magnetic fields might provide protection against stellar wind and charged particle flux. Earth's magnetic field demonstrably shields our atmosphere from solar wind erosion and reduces surface radiation exposure. If red dwarf planets could generate comparable fields, perhaps they could maintain habitable conditions despite hostile stellar environments. This proposal faces immediate challenges from orbital mechanics. Planets in red dwarf habitable zones orbit so close to their stars that tidal forces lock their rotation to their orbital period. This synchronization prevents the differential rotation that drives Earth's magnetic dynamo. Tidally locked planets probably cannot generate strong magnetic fields through the same mechanism that protects Earth. Alternative dynamo mechanisms might operate in tidally locked planets, but theoretical models suggest these would produce weaker and less stable fields than Earth possesses. Even if some magnetic protection existed, it would need to exceed Earth's field strength by substantial factors to compensate for the enhanced stellar wind pressure at close orbital distances. The physics does not favor this outcome. Thick atmospheres might absorb radiation before it reaches planetary surfaces. Venus demonstrates that dense atmospheres can block most incoming radiation while maintaining surface conditions dramatically different from what direct stellar heating would produce. Perhaps red dwarf planets with sufficiently massive atmospheres could shield their surfaces from stellar assault. This proposal ignores the atmospheric erosion documented in the previous section. The same stellar activity that thick atmospheres would need to block also strips those atmospheres away over geological timescales. Building atmospheric protection against a threat that simultaneously destroys the protection creates an unwinnable situation. Even if atmospheric erosion could somehow be prevented, thick atmospheres present their own habitability challenges. Dense carbon dioxide atmospheres like Venus possesses create surface temperatures incompatible with liquid water. Hydrogen-rich atmospheres that might resist erosion better than Earth-like compositions would create reducing chemical environments, unlike anything terrestrial biology evolved to tolerate. Subsurface oceans might shield organisms from even the most intense stellar activity. Europa and Enceladus in our own solar system demonstrate that liquid water can exist beneath icy crusts far from stellar habitable zones. Perhaps red dwarf planets could maintain similar subsurface environments protected from surface radiation by kilometers of ice or rock. This proposal has merit for preservation of simple life that somehow emerged elsewhere and was transported to protected environments. But it fails to explain how life could originate in subsurface isolation. Prebiotic chemistry requires energy inputs that subsurface environments may not provide in sufficient quantity. Life on Earth apparently required surface or near-surface conditions during its origin, only later colonizing deep subsurface niches. Furthermore, cosmic ray penetration reaches depths that would compromise even subsurface refugia around active red dwarfs. The particle fluxes documented earlier penetrate through kilometers of shielding material. No depth accessible to liquid water provides complete protection from the radiation environment that red dwarfs create. Extremophile biology might evolve tolerance to radiation levels fatal to Earth organisms. Terrestrial life includes organisms capable of surviving conditions that would kill most species. Deinococcus radiodurans tolerates acute radiation doses thousands of times higher than human lethal limits. Perhaps evolution around red dwarfs could produce organisms with even greater radiation resistance. This proposal confuses survival of acute exposure with tolerance of chronic exposure. Radiation-resistant organisms on Earth evolve their capabilities in environments where radiation arrives in brief pulses separated by long recovery periods. They repair damage between exposures using cellular machinery that requires time and resources to function. Continuous radiation exposure at the levels red dwarfs deliver would overwhelm any conceivable repair mechanism. Damage would accumulate faster than any biology could correct it. Even if organisms evolved extraordinary repair capabilities, maintaining those capabilities would consume energy that could not be devoted to growth, reproduction, or other biological functions. The proposed solutions consistently underestimate the problem because they address individual threats rather than their combination. A magnetic field that blocks stellar wind does not stop electromagnetic radiation. An atmosphere that absorbs ultraviolet flux still erodes under particle bombardment. Subsurface oceans that survive cosmic rays still require chemical inputs from surfaces exposed to stellar assault. Proxima Centauri taught us that red dwarf habitability is not a single problem with potential solutions, but rather a constellation of interlocking problems that compound each other's effects. Solving one aspect of stellar hostility accomplishes little when other aspects remain overwhelming. The threats operate simultaneously, reinforcing each other through physical mechanisms that cannot be addressed individually. This lesson generalizes to red dwarfs throughout the galaxy. The specific numbers differ from star to star. Activity levels vary across the population according to stellar mass, age, and rotation rate. But the fundamental pattern of continuous environmental assault appears wherever we look with sufficient sensitivity to detect it. The danger was never the planet. The danger was always the star. This framing inverts how we typically think about habitability. We ask whether planets have the right characteristics for life, while treating stellar environment as fixed background. We catalogue planetary masses, orbital distances, and atmospheric compositions. We calculate surface temperatures and assess geological activity. We devote enormous resources to characterizing planetary properties, while largely ignoring what the parent star does to surrounding space. The red dwarf evidence suggests we should ask first whether stars create environments where planetary characteristics matter. A world with perfect temperature, perfect chemistry, and perfect geological activity remains uninhabitable if its star continuously destroys the conditions that allow life to function. The best possible planet cannot overcome a fundamentally hostile stellar environment. Proxima Centauri b may possess every planetary attribute we associate with habitability. Its orbital distance places it within the temperature range where liquid water could exist. Its position around our nearest stellar neighbour made it an attractive target for detailed characterization. None of these planetary properties matter because of what the star does. Proxima Centauri b remains definitively hostile to biology, not because of any planetary failing, but because its star has processed surrounding space into an environment where life cannot function. The planet might be perfect. The star ensures that perfection is irrelevant. The observational biases that delayed recognition of this truth operated at multiple levels simultaneously. Each bias alone might have been overcome through ordinary scientific self-correction. Together, they created a systematic blind spot that persisted for decades. Short-term monitoring missed cumulative effects that only become apparent over decades or centuries of stellar activity. Telescope time is precious and expensive. Allocation committees favor projects that promise results within funding cycles measured in years. Proposals for multi-decade monitoring campaigns face skepticism about whether they represent good use of limited resources. This temporal bias ensured that our understanding of Proxima Centauri derived from snapshots rather than sustained observation. We characterized the star based on brief windows that might or might not represent typical behavior. Statistical extrapolation from limited data produced estimates that consistently understated the true activity level. Visible light observations missed the high-energy emissions that do the most damage to planetary environments. Ground-based telescopes dominated early characterization efforts. These instruments excel at measuring visible light, but cannot detect X-rays, gamma rays, or extreme ultraviolet radiation that Earth's atmosphere blocks. The wavelengths most relevant to habitability assessment remained invisible to the instruments most commonly used. Space-based observatories capable of detecting high-energy emissions came later and received less observation time than ground-based facilities. Competition for satellite telescope access is intense. Proposals focused on nearby red dwarfs competed against projects studying more exotic objects that promised higher-profile discoveries. Solar-centric models interpreted red dwarf data through inappropriate frameworks. Astronomers trained on solar physics naturally applied solar concepts to other stars. The Sun provided the template for understanding stellar behavior because it was the only star we could study in detail. Deviations from solar patterns seemed like exceptions requiring explanation rather than evidence of fundamentally different physics. This framework bias caused researchers to interpret red dwarf activity as enhanced solar behavior rather than qualitatively different phenomena. A red dwarf flare was understood as an extreme solar flare rather than as a fundamentally distinct event arising from different magnetic field configurations. The models that guided interpretation embedded assumptions that prevented accurate characterization. Institutional incentives rewarded discovery of potentially habitable planets over characterization of stellar hostility. Finding an Earth-like planet generates media attention, public interest, and subsequent funding. Documenting why that planet cannot actually support life generates less enthusiasm despite equal or greater scientific importance. Career advancement in astronomy depends partly on visibility and citation counts. Papers announcing exciting discoveries attract more attention than papers explaining why those discoveries matter less than initially claimed. Researchers responding rationally to incentive structures naturally gravitated toward optimistic framings that maximized professional benefit. Each bias reinforced the others through feedback loops that resisted correction. Researchers who pointed out problems with red dwarf habitability faced skepticism because the evidence supporting their concerns remained incomplete. Building complete evidence required sustained investment in long-term monitoring and high-energy observations. Funding agencies hesitated to provide such investment when prevailing assumptions suggested the problem was not severe. The scientific community eventually accumulated enough evidence to force reassessment. But the process took decades longer than it should have because we actively resisted conclusions we did not want to reach. We wanted Proxima Centauri to be friendly. We wanted red dwarf planets to be habitable. We wanted the galaxy to be full of potential homes for life. Reality does not accommodate our preferences. Proxima Centauri behaves according to physics rather than human hopes. The star's violence reflects its internal structure and energy transport mechanisms. Those mechanisms operated the same way 4 billion years ago when the star was young. They operate the same way today. They will continue operating the same way for trillions of years into the future. This temporal persistence matters profoundly for any consideration of life around red dwarfs. Red dwarfs burn their nuclear fuel so slowly that they remain on the main sequence for timescales exceeding the current age of the universe. Our Sun will exhaust its hydrogen fuel in approximately 5 billion years, expanding into a red giant that will engulf the inner planets. Proxima Centauri will still be steadily burning hydrogen when our Sun has become a cooling white dwarf remnant. The hostility we observe today will persist indefinitely on any timescale relevant to biological evolution. There is no future epoch when conditions around Proxima Centauri will become benign. There is no waiting out the stellar violence in hope of calmer times. The star is what it is, and will remain so for longer than the universe has yet existed. If anything, red dwarf activity may intensify over cosmic time, rather than diminishing. Some theoretical models suggest that magnetic field strength and flare frequency increase as these stars slowly contract over billions of years. Faster convection generates stronger magnetic fields. Stronger fields produce more intense flares. The Proxima Centauri of the far future might be even more violent than the star we observe today. A planet that somehow survived current conditions would face worsening rather than improving circumstances over geological timescales. The trajectory points toward increasing hostility rather than gradual moderation. This persistence means that any life emerging around red dwarfs faces not temporary challenges, but permanent environmental conditions. There is no calm period billions of years ago when life might have established itself before conditions worsened. Red dwarfs have been actively flaring since they ignited. The early universe contained red dwarfs, just as hostile as those we observe today. There is no future calm period when conditions might improve enough to permit biological development. The physics that drives red dwarf activity will continue operating until these stars exhaust their fuel trillions of years hence. The hostility represents the fundamental nature of these stellar objects, not a temporary phase they will eventually outgrow. The philosophical implications of this recognition deserve direct acknowledgement. We live in a universe where the most common type of star creates conditions that prevent life from existing around it. 70% of stellar objects in our galaxy generate environments of continuous violence, incompatible with the chemistry that produces biology. The vast numerical majority of star systems cannot host living worlds, regardless of what planets orbit within them. This revelation challenges optimistic assumptions about cosmic habitability that have dominated scientific and popular imagination for decades. The Drake equation, that famous attempt to estimate the number of technological civilizations in our galaxy, includes terms for the fraction of stars with planets and the fraction of planets where life develops. Those terms implicitly assume that stellar environments do not preclude biology. Removing 70% of stars from habitability consideration does not merely adjust the Drake equation by a factor of 3. The equation asks what fraction of suitable stars host life without adequately defining what makes a star suitable. Red dwarf hostility suggests that suitability requirements are far more restrictive than previously assumed. The galaxy is not teeming with potential homes for life. Most stellar environments are hostile. Most planets orbit stars that actively destroy habitability. Most of the universe may be permanently and fundamentally dead regardless of how favorable local chemistry might otherwise be. This assessment might seem pessimistic, but pessimism and accuracy are not opposites. A realistic understanding of cosmic habitability serves science better than optimistic speculation that eventually requires correction. The sooner we accept what red dwarf studies reveal, the sooner we can redirect resources toward the stellar environments where life might actually exist. The stars that could potentially host life represent a minority of stellar populations. Sun-like stars are rare compared to red dwarfs. G-type stars like our Sun constitute only about 7% of the galactic stellar population. Adding K-type stars, which are somewhat smaller and cooler than the Sun, but potentially less hostile than red dwarfs, increases the fraction to perhaps 15%. Even among these more promising stellar types, many exhibit activity levels that would challenge planetary habitability. Young stars of all types show enhanced magnetic activity during their first billion years. Binary star systems create gravitational environments that may destabilize planetary orbits. Stars that vary significantly in luminosity prevent the stable conditions that biological evolution apparently requires. The subset of stars creating genuinely friendly environments may be vanishingly small. Perhaps a few % of stars provide the calm, stable radiation environments that life requires. Perhaps even fewer when all relevant factors are considered. The universe may contain far fewer potential homes for biology than optimistic estimates have suggested. This does not mean life is absent from the universe. It means life probably concentrates around relatively unusual stars that happen to provide stable environments over billions of years. Our Sun may be far more special than we appreciated when we assumed all stars behaved similarly. The Sun's relative calm reflects its internal structure. The radiative zone, separating the Sun's core from its convective envelope, creates conditions for organized magnetic field generation through the solar dynamo. This organization produces the 11-year activity cycle that modulates solar behavior in predictable patterns. The overall activity level remains low enough that Earth has maintained a stable biosphere for billions of years. Red dwarfs lack this structural organization. Their fully convective interiors generate magnetic fields through turbulent processes that produce chaotic activity patterns. The Sun's behavior represents not the stellar norm, but a fortunate exception that enabled life to develop on at least one of its planets. We may owe our existence partly to the accident of orbiting an unusually well-behaved star. Had the Sun formed as a red dwarf, which the stellar initial mass function suggests was statistically more likely, Earth would never have developed conditions suitable for biology. The chain of circumstances, leading from stellar formation to intelligent observers, includes the requirement for a sufficiently calm stellar environment. This realization connects to broader questions about cosmic fine-tuning and the conditions necessary for observers to exist. The universe appears configured in ways that permit complexity to emerge, but only in restricted locations where multiple favorable conditions coincide. Life may require not just the right chemistry and the right planetary properties, but also the right stellar environment. A combination of requirements that dramatically limits where biology can appear. The mischaracterization of Proxima Centauri ultimately reflects a broader tendency to project familiar experiences onto unfamiliar phenomena. We know one star intimately. We extrapolated that knowledge to stars we barely understood. When different types of stars turned out to behave differently, we struggled to accept evidence that contradicted our expectations. This cognitive pattern will likely recur as we explore the universe further. Each time we do so, we risk the same kind of systematic error that delayed our understanding of red dwarf hostility. The lesson from Proxima Centauri extends beyond stellar astrophysics. We must approach cosmic phenomena with genuine openness to discovering properties that contradict our assumptions. We must invest in sustained observation rather than brief surveys that sample behavior inadequately. We must integrate knowledge across disciplinary boundaries rather than compartmentalizing inconvenient findings that challenge preferred narratives. Our nearest stellar neighbor has been teaching this lesson for over a century. We are only now beginning to learn it. The star that appeared so dim and harmless has turned out to be one of the most hostile environments in our cosmic neighborhood. The danger was never hidden in some exotic wavelength, awaiting discovery by future instruments. It was never mysterious, encoded in phenomena beyond current theoretical understanding. It was never waiting to be discovered through some future breakthrough that would suddenly reveal what had been invisible. The danger was always present in every observation we made, in every physical model we constructed, in every theoretical framework we developed. The flare detections of the 1950s documented violence we chose to minimize. The X-ray observations of the 1990s revealed hostility we chose to compartmentalize. The comprehensive monitoring of the 2000s confirmed patterns we chose to rationalize away. We simply refused to see what was there, because seeing it would have required abandoning comforting illusions about cosmic habitability and human cosmic significance. We wanted to believe that living worlds might exist practically next door. We wanted to believe that the universe was friendly to life, that habitable environments were common, that we would eventually find cosmic companions not so different from ourselves. We wanted to believe that our search for meaning in a vast and indifferent cosmos might succeed through the discovery of other minds struggling with similar questions. Finding life around our nearest stellar neighbor would have validated hopes that we are not alone, that intelligence is a common outcome of cosmic evolution, that the universe tends toward the emergence of observers who can appreciate its grandeur. Proxima Centauri does not care what we want to believe. The star continues flaring multiple times per day. The stellar wind continues eroding any atmosphere in its path. The baseline radiation continues bathing, surrounding space in lethal doses. The cumulative processing continues transforming any nearby world into an environment where biology cannot function. This has been true for billions of years before humans evolved. It will remain true for trillions of years after our species is gone. The mischaracterization was always ours. The truth was always there, written in photons and particles that we collected, but failed to understand, because understanding would have required accepting conclusions we found emotionally difficult. We finally see our closest stellar neighbor for what it is, not a dim, harmless ember floating peacefully through nearby space, not a potential host for alien life waiting to be contacted, not a friendly destination for future human exploration, or the first target for interstellar probes seeking evidence of extraterrestrial biology. Proxima Centauri is a furnace of violence wrapped in apparent dimness, a source of continuous destruction operating through mechanisms we spent decades overlooking because they contradicted narratives we preferred, a reminder that cosmic environments do not exist to accommodate human hopes, and that the universe operates according to physics rather than narrative convenience. The closest star beyond our sun is hiding nothing. It never was. We simply looked away from what was always in plain sight, convinced ourselves that small meant harmless, and built optimistic dreams on foundations of systematic misunderstanding. The truth requires no dramatic revelation. It requires only honest acknowledgement of evidence that has accumulated for generations. Our nearest stellar neighbor has always been hostile. We are only now willing to admit it. This admission marks not the end of scientific inquiry into red dwarf habitability, but a new beginning grounded in accurate understanding. Future research will refine our knowledge of how red dwarf activity varies across the stellar population. Some stars may prove less hostile than Proxima Centauri, even if none prove genuinely benign. Theoretical models will improve as observations constrain the physics of magnetic field generation in fully convective interiors. But the fundamental conclusion will not change. Red dwarfs as a class create conditions incompatible with life as we understand it. The 70% of stars in our galaxy that belong to this category do not host habitable worlds. The search for extraterrestrial life must focus elsewhere, on the minority of stars that provide environments where biology can emerge and persist. This narrowing of the search may ultimately prove fortunate. Concentrating resources on the most promising targets rather than spreading effort across all possibilities increases the likelihood of eventual success. Understanding where life cannot exist helps clarify where it might. The hostile truth about red dwarfs points toward the friendlier truth about other stellar types. Proxima Centauri remains scientifically valuable despite its hostility. As our nearest stellar neighbor, it provides the best available laboratory for studying red dwarf physics in detail. Every observation teaches us something about how these common stars behave. That knowledge applies across the galaxy to the billions of similar objects we cannot study with comparable resolution. The star's proximity also makes it a natural target for future interstellar missions, regardless of habitability considerations. Breakthrough Starshot and similar initiatives aim to send probes to the Alpha Centauri system within decades. Those probes will return data about Proxima Centauri's environment that no Earth-based observation can provide. Direct measurements of stellar wind properties, radiation environments, and planetary surface conditions will refine our understanding even further. But those missions will not discover unexpected habitability. They will confirm what decades of observation have already established. Proxima Centauri is hostile. Its planets are not places where life can exist. The violence we document from 4 light-years away operates even more intensely at the close ranges, where spacecraft instruments will eventually collect data. The story of Proxima Centauri is ultimately a story about human cognition and its limitations. We are pattern-matching creatures who interpret new information through frameworks built from past experience. This cognitive architecture serves us well in familiar environments where past experience provides reliable guidance. It fails us when we encounter genuinely novel phenomena that do not fit established categories. Red dwarfs were genuinely novel to astronomers trained on solar physics. The Sun provided the only detailed template for stellar behavior. Applying that template to fundamentally different objects produced systematic errors that persisted until evidence became overwhelming. The same cognitive limitations will likely produce similar errors as we explore further into cosmic environments that differ even more dramatically from terrestrial experience. The correction for this limitation is not superhuman objectivity that no individual can achieve. It is institutional structures that encourage skepticism toward preferred conclusions, reward documentation of inconvenient findings, and integrate knowledge across disciplines that might otherwise remain isolated. Building such structures is difficult. The Proxima Centauri mischaracterization demonstrates what happens when we fail. Our nearest stellar neighbour spent a century teaching us about our own limitations as observers and interpreters of cosmic phenomena. The tuition was expensive, measured in decades of misdirected research and public misunderstanding about cosmic habitability. But the lesson, once learned, applies far beyond a single star to every future encounter with the genuinely alien. The universe contains wonders beyond imagination. It also contains horrors that wear innocent disguises. Learning to distinguish between them requires abandoning the assumption that cosmic environments will conform to human hopes. Proxima Centauri looked like a friendly neighbour. It was always a hostile one. We simply refused to see what was always there. Now we see. The question is, what we do with that vision.